When the James Webb Space Telescope turned its eyes toward a nearby young star named HR8799, scientists were stunned by what it revealed. Circling this star, just 133 light-years away, are four massive alien planets, each bigger than Jupiter, moving in graceful orbits that defy what we thought we knew about how planetary systems form. This wasn't a guess or a simulation. Webb actually saw these planets, directly capturing their presence and movement. That alone is groundbreaking because very few planets outside our solar system have been imaged directly. Most are detected by subtle shifts in light, not with actual pictures. But here, Webb delivered visuals of an alien solar system in action. HR8799 isn't just any star. It's young, hot, and about 1.5 times the mass of our Sun. This star has long fascinated astronomers because its four giant planets had already been spotted years ago using ground-based telescopes like Keck and Gemini. But those telescopes had limitations: blurry resolution, less precision, and atmospheric interference from Earth. Webb, floating far beyond our planet's atmosphere, offered a new level of clarity. And when it focused on HR8799, it saw details that had never been visible before. Not only did it confirm the existence of all four planets, but it also revealed finer aspects of their atmospheres, motion, and potential for moons or even rings. Each of these planets is a gas giant, meaning they're made mostly of hydrogen and helium like Jupiter and Saturn. But these planets are far more massive, ranging from 5 to 10 times Jupiter's mass. They orbit much farther from their star than we might expect. The closest one is about 14 times the Earth-Sun distance, and the farthest sits nearly 70 times farther out. That's well beyond the orbit of Pluto in our solar system. Yet all four planets maintain stable orbits, suggesting a delicate gravitational dance that has persisted for tens of millions of years. It's like watching a cosmic ballet, choreographed by the invisible hand of gravity. Webb's advanced infrared sensors played a crucial role in this discovery. Infrared light can pierce through dust and gas that would block visible light, making it perfect for studying distant star systems. When Webb observed HR8799, it didn't just see glowing orbs, it analyzed the light coming from each planet. And from those light signatures, scientists could identify key molecules in the planet's atmospheres. Methane, water vapor, carbon monoxide, all these elements were found swirling around the giant planets. These are the same molecules that exist in the atmospheres of gas giants in our own solar system. But seeing them in an alien system proves that the building blocks of planetary atmospheres may be more universal than we thought. One of the most exciting outcomes from this observation is the possibility that some of these planets could host moons. We can't see the moons directly yet, they're too small and too close to their host planets. But Webb picked up hints in the light curves and in the way the planet's gravity affects surrounding dust. If these planets have moons, and if those moons have atmospheres or liquid water, they could become prime candidates in the ongoing search for life beyond Earth. We're talking about worlds orbiting worlds, moons circling giant planets in another solar system entirely. It sounds like science fiction, but it's very much real. What makes HR8799 even more intriguing is that it seems to be a young version of what our own solar system might have looked like in its early days. Scientists estimate the star is just 30 to 60 million years old, a newborn in cosmic terms. That means we're watching these planets during their developmental phase. They're still hot from their formation, still adjusting to their orbits, and possibly still collecting material. This gives scientists a rare opportunity to study planetary evolution as it happens. It's like seeing a baby picture of a solar system, but in stunning detail that offers clues to how our own world came to be. And then there's the question of how such massive planets ended up so far from their star. Traditional models of planetary formation suggest that big planets should form closer in where there's more material. Yet HR8799's giants are way out in the outer reaches of the system. This forces scientists to rethink their theories. Maybe planets migrate outward after forming. Maybe there's a new mechanism we haven't discovered yet. Webb's data doesn't just give us answers. It pushes us to ask better, deeper questions about how solar systems come together and evolve over time. The outermost planet in this system, named HR8799b, is especially mysterious. At nearly 7 times the mass of Jupiter, it has an atmosphere filled with clouds of dust, methane, and possibly silicates, tiny particles of rock that could create a kind of alien smog. Webb's instruments detected unexpected variations in the light from this planet, suggesting dynamic weather patterns, possibly even giant storms or turbulent jet streams. This hints at a wildly active atmosphere, far more chaotic than anything we've seen in our own system. Imagine Jupiter's Great Red Spot, but 10 times bigger and moving across an alien sky. Another fascinating point is how these planets maintain stability despite their size and spacing. In our solar system, massive planets like Jupiter and Saturn help stabilize the orbits of smaller planets. But if you put 4 Jupiters in wide, spaced-out orbits, you might expect gravitational chaos. Yet the HR8799 system seems to be in perfect balance. Scientists believe the planets are locked in a rare orbital resonance, a pattern where their movements are synced in just the right way to prevent collisions or instability. It's like a 4-part harmony in music, where each note complements the others perfectly. The Webb observations also showed that these planets reflect and absorb light in different ways. That suggests each has a unique composition, despite forming around the same star. Some have thicker clouds, some are hotter, and some show evidence of carbon-based compounds. This diversity makes HR8799 a natural laboratory for studying planet types. Why do planets in the same system turn out so different? Is it their position, their age, or some hidden variable we haven't identified yet? With each answer Webb gives us, another question rises from the cosmic mist. One of the biggest implications of this discovery is its effect on the search for habitable worlds. If a system like HR8799, with giant planets far from their star, can exist so close to Earth, how many others are out there? If Webb can directly image planets in this system, it can do the same for others, maybe even for smaller, rocky planets in tighter orbits. The technology that captured these alien giants is the same technology that could one day reveal an Earth twin orbiting a nearby star. And that possibility changes everything. This kind of direct imaging used to be a dream. Now it's happening. We're no longer guessing what other systems might look like, we're seeing them, measuring them, and studying them in real time. It's a turning point in astronomy, made possible by years of work, billions of dollars, and the collective curiosity of thousands of people around the world. Webb is showing us not just what's out there, but how we fit into the grand structure of the cosmos. And HR8799, with its 4 giant alien planets, is just the beginning. As scientists dig deeper into the data collected by the James Webb Space Telescope, HR8799's 4 alien planets continue to raise more eyebrows. One of the key advantages of Webb is its ability to detect and analyze infrared light with incredible precision. This light carries important information about the temperature and chemistry of celestial bodies. For the planets in the HR8799 system, Webb's instruments revealed temperatures ranging from 800 to 1200 Kelvin, hot enough to melt many metals on Earth. These aren't cool, dead worlds, they are hot, active, and chemically rich. And that means they're far from simple gas balls, they're complex and dynamic, with evolving atmospheres and potential internal activity. What makes these findings even more valuable is that Webb can observe changes over time. Scientists are planning to revisit HR8799 regularly to look for long-term changes in brightness, motion, and atmospheric composition. That opens up a new window into how gas giants evolve over time. Imagine being able to watch the weather on a planet 133 light-years away, storms forming, clouds shifting, and sunlight filtering through exotic chemicals. That's what Webb is now capable of, and HR8799 is becoming a testbed for this kind of deep atmospheric science. The Webb team also noticed something fascinating about the light being reflected from the planets. Some of it appears polarized, which is a clue about the structure of the clouds in their atmospheres. Polarized light is usually scattered in a specific way by small particles, like the dust and ice crystals found in clouds. This gives astronomers more tools to build models of what these alien atmospheres actually look like. Are they covered in swirling bands like Jupiter? Do they have towering storms like Saturn? Or are they unlike anything we've ever seen? Webb's data is helping scientists build these 3D models in unprecedented detail. One of the big surprises from the Webb observations is the apparent absence of certain expected features. For example, in some planets, the levels of methane were far lower than predicted. That doesn't mean the data is wrong, it means our understanding of gas giant chemistry might be incomplete. Methane should form easily in the outer parts of giant planets, especially if they are cool. But the HR8799 planets seem to defy this expectation. That could point to unexpected atmospheric dynamics, internal heat sources, or even unknown chemical reactions taking place high in the clouds. Webb is forcing scientists to go back and refine their models, because the universe, as always, is stranger than we thought. What's even more compelling is that the system isn't isolated. HR8799 is surrounded by a massive dusty disk, similar to the Kuiper belt in our own solar system but much thicker. This disk is made of rock, ice, and other debris left over from the planet-forming process. And just like in our solar system, This debris can be influenced by the gravity of the giant planets. Webb is helping scientists trace how the planets interact with this disk, sculpting it, clearing gaps, and possibly sending comets inward toward the star. These interactions hint at a dynamic system where new objects might still be forming or migrating, and that kind of activity is rarely seen with such clarity. Then there's the question of timing. Why is this system so stable despite being so young and chaotic? Usually, young systems are marked by instability, planets crashing into each other, orbits shifting wildly, and debris flying in all directions. Yet HR8799's planets appear to be locked in a kind of cosmic rhythm. Their orbits are in what scientists call a mean motion resonance, where the timing of each orbit is perfectly synchronized with the others. This resonance keeps them from colliding or drifting too close to the star. It's as if the universe hit the perfect beat, and these planets are dancing to it without missing a step. This stability also raises the possibility that smaller, Earth-sized planets could exist in the inner parts of the system, hidden from view for now. Webb can't see them yet, but its future missions, combined with other telescopes, might. If such planets exist, they would likely sit in the habitable zone of the star, the region where temperatures are just right for liquid water to exist. That's the holy grail in exoplanet research, a planet that's not just Earth-like in size but also in conditions. And while HR8799 is still a young system, its structure suggests it might be capable of supporting such planets in the future. Beyond the science, there's also something deeply emotional about these discoveries. For centuries, humans looked up at the stars and wondered if other worlds were out there. Now, with the help of the James Webb Space Telescope, we're not just finding those worlds, we're studying their weather, their chemistry, even their cloud patterns. These four alien giants are more than just scientific data points. They're real places orbiting a real sun in a real solar system. And the fact that we can observe them from such an incredible distance is a testament to how far we've come as a species. The HR8799 system is also a major validation of the Webb telescope's capabilities. When the telescope was launched, there were hopes and expectations but also a lot of pressure. Could it really do what it was built to do? Now, with discoveries like this, there's no doubt left. Webb is not just meeting expectations, it's exceeding them. And this is just one star, one system. There are thousands more waiting in the telescope's queue. Each one could hold surprises just as dramatic, just as revolutionary. HR8799 might be the first system to be captured in such detail, but it won't be the last. Scientists are now planning follow-up observations with Webb and other telescopes to learn even more about this fascinating system. They'll look for signs of planetary migration, how the planets may have moved from where they first formed. They'll study the star itself in more detail, to see how its radiation influences the atmospheres of its planets. And they'll keep hunting for hidden companions, smaller planets, moons, or even rings that might still be lurking in the background. The more we look, the more we'll find. And every new discovery will add another piece to the grand puzzle of how planets and solar systems come to be. Perhaps the most inspiring thing about this discovery is what it tells us about our place in the universe. The HR8799 system is young, but in time it could develop rocky planets, complex chemistry, and maybe even life. We're watching the early stages of a story that could unfold into something as rich and diverse as our own planetary neighborhood. And that reminds us that Earth is not unique, not in its structure, not in its potential, and maybe not even in its life. The more we see systems like HR8799, the more we realize that planets are not rare, they're common. And if planets are common, then maybe life is too. The James Webb Space Telescope has only begun its journey. HR8799 is one of its first major exoplanet targets, but there are hundreds more lined up, each with their own secrets. Some may host super-Earths, others may hide ocean worlds, and a few might even show biosignatures, chemical clues that hint at living organisms. Webb is the most powerful eye we've ever sent into space, and it's already transforming our understanding of the cosmos. With each observation, we're moving one step closer to answering the oldest question of all. Are we alone? For now, HR8799 stands as a beacon of what's possible. A star not so far away, surrounded by giant planets with exotic atmospheres and mysterious orbits. Thanks to the James Webb Space Telescope, we're no longer just looking up at the stars, we're reaching out, one system at a time, into the vast, unknown frontier of space.
The nature of neutron stars is their high spin rate. Due to the conservation of angular momentum during the star's collapse, a neutron star can spin hundreds of times per second. This rapid rotation gives rise to powerful jets of radiation that shoot out from the poles of the neutron star, emitting radiation at various wavelengths, including radio waves, X-rays, and gamma rays. Some rapidly rotating neutron stars emit beams of radiation that sweep across space, like a lighthouse, a phenomenon that gave birth to the term pulsar. Neutron stars can also form in binary systems, where two neutron stars, or a neutron star and a white dwarf, orbit each other. When a neutron star merges with another compact object, it can form a strange object known as a quark star. Instead of a traditional core made of neutrons, a quark star consists of a core made of quarks. These particles can combine to form mesons, which in turn bind to other quarks, creating a stable, extremely dense form of matter. While quark stars are highly speculative, they remain an interesting idea among astrophysicists. Black holes, on the other hand, are regions of space-time where gravity is so strong that nothing, not even light, can escape their grasp. They form when massive stars collapse at the end of their life cycle. Similar to neutron stars, the collapse of a star into a black hole begins with the exhaustion of nuclear fuel, leading to a loss of outward pressure. Without the pressure to support itself, the core collapses under the force of gravity. As the core continues to collapse, it reaches a critical point called the Schwarzschild radius, which defines the size of the black hole's event horizon. Beyond this radius, the gravitational pull becomes inescapable. A black hole's defining property is its event horizon, the boundary beyond which nothing can escape. It's not a physical surface, but a region in space from which nothing can return. Inside the event horizon, the gravitational pull becomes increasingly strong until it reaches an infinitely dense point known as the singularity. The singularity is a region of space-time where matter is compressed to infinite density, and our current understanding of physics breaks down. The boundary of the event horizon can be thought of as the point of no return. Once something crosses this boundary, it cannot escape the black hole's grasp and will inevitably be pulled toward the singularity. One unique aspect of black holes is that their properties can be measured indirectly by observing their effects on nearby matter. As matter approaches a black hole, it accelerates and heats up dramatically, emitting intense radiation that can be detected by telescopes. This radiation, known as synchrotron radiation, provides valuable information about the black hole's mass, spin, and the characteristics of the accretion disk. Accretion disks are swirling disks of glowing hot gas and plasma that form around black holes. As matter falls into a black hole, it forms an accretion disk where it heats up to millions of degrees. This heated matter emits radiation across the electromagnetic spectrum, making accretion disks visible to astronomers. The study of accretion disks provides insights into the physics of matter under extreme conditions and helps us understand the evolution of galaxies. Jets are powerful beams of radiation that shoot out from near the poles of rotating black holes. Powered by the rotational energy of the black hole, these jets can extend for thousands of light years, influencing the formation of large-scale structures in galaxies. Jets play a crucial role in galaxy evolution and have been observed in active galactic nuclei and many other types of black hole systems. Finally, gravitational waves are ripples in the space-time fabric that can be generated by the acceleration of massive objects. When two black holes merge, they release a burst of gravitational waves, carrying a significant amount of energy. Gravitational wave astronomy has opened a new window to observe the universe, allowing us to detect events such as black hole mergers. Now let's compare their fighting styles. First, their weaponry. Both neutron stars and black holes use gravity as their primary weapon. However, a black hole's gravity is much more powerful due to its larger mass and the absence of an event horizon. Anything that ventures too close is trapped forever and inexorably drawn towards the singularity. On the other hand, a neutron star's gravity, while strong, is less extreme. It's a force to be reckoned with, but it lacks the all-consuming power of a black hole. In terms of offensive capabilities, neither has a real means of striking physically. They only manipulate gravity. However, a black hole could theoretically attack by gradually tearing a neutron star apart, bit by bit, over a long period of time. A neutron star, however, cannot really attack because it is held up by the same gravity that would draw it into a black hole. However, its last-ditch defense is to emit a burst of radiation from its poles to repel a black hole. But against a hungry black hole, this would probably have little effect, unless it is accompanied by a well-aimed gravitational wave blast. So we can say that a black hole has the advantage in terms of weaponry. Their gravitational manipulation is far more devastating than that of a neutron star. As for their defenses, neutron stars have one major advantage. Their hard outer crust acts as a shield, protecting them from external attacks. This outer layer of tightly packed neutrons and protons can withstand incredible forces without breaking apart. On the other hand, a black hole has no real defense. Its event horizon marks the boundary beyond which nothing can escape. Once anything crosses this point, it's doomed to be pulled into the singularity. A black hole's lack of physical substance leaves it vulnerable to attacks from all sides. In terms of speed, neutron stars are incredibly fast. Thanks to their rapid rotation, they can spin hundreds of times per second, covering vast distances in a short amount of time. Black holes, on the other hand, can't move at all except to orbit in a straight line. They don't have a physical body that can rotate or move independently, while a black hole can influence its surroundings through gravity, and its event horizon can expand and contract. It cannot move in space. Finally, let's look at their intelligence. Neither of these celestial objects is considered intelligent in the traditional sense. They do not possess consciousness, emotions, or the ability to plan or execute complex actions. However, they respond to their environment in predictable ways, governed by the laws of physics. A black hole will always pull in matter and energy towards its event horizon, while a neutron star will always spin and emit radiation from its poles. While not intelligent, these responses can be studied and understood by astronomers, allowing them to learn more about the universe. So who would win in a fight to the death? Well, given their strengths and weaknesses, it's clear that the winner would be the black hole. Its superior gravitational abilities, lack of vulnerability, and potentially hostile approach would likely overwhelm the neutron star's defenses. It's important to remember that this is just a hypothetical battle. In reality, such an encounter would depend on various factors, like the relative masses and speeds of the objects, but in a one-on-one showdown, the black hole's power would likely prevail, and here's why. A black hole's event horizon is essentially a boundary that the neutron star would need to cross to reach the singularity. If the neutron star were to collide with the event horizon, the gravitational forces involved could be so intense that the neutron star would be stretched and distorted in a process known as spaghettification. The gravitational forces would pull the neutron star into a long, thin shape similar to spaghetti. Once the neutron star is completely within the event horizon, it would continue to be pulled towards the singularity, crossing the boundary of no return. Eventually, the neutron star would reach the singularity, where it would be compressed to infinite density. So the black hole would devour the neutron star, piece by piece, slowly unraveling it until it is no longer a recognizable object. Now imagine you're a tiny spacecraft, floating past a black hole, and suddenly find yourself face to face with a neutron star. How would you escape this deadly situation? Share your thoughts in the comments below. Here's one final thought. Sometimes when I'm staring into the vast abyss of space, I can't help but wonder if there's more to this universe than meets the eye. Like, are we just a blip on the radar of some cosmic consciousness? Or is there a higher purpose to all of this? If I had to guess, I'd say that the universe doesn't care about us. It's not personal, just indifferent. But hey, maybe that's where you come in. What do you think? Does the universe have a greater plan for us? Or are we just along for the ride? Let me know in the comments below. And hey, thanks for watching. I know there are plenty of other videos out there, but you chose this one.